Hi everyone, this is Miss Leia, and in this video, we're going to talk about freely falling bodies. So basically, we're just going to describe what is meant by freely falling bodies, and then we'll also talk a bit about the problem-solving steps for freely falling bodies, but not yet too detailed. So first thing you have to know, when you say that the object is in a state of free fall, the effects of the air on the object can be neglected. Okay, let's say for example, a sheet of paper, if you allow it to fall down, obviously it's going to sway at random directions, so it's obviously affected by air resistance. Therefore, a sheet of paper is not in a state of free fall. But if you make it crumpled, for example, crumpled piece of paper, it can be in a state of free fall because it can ignore air resistance. It will fall straight down. Therefore, that could be an example of a freely falling body, especially if the height is not really high. Let's say, for example, from your waist down, you let a crumpled paper drop. It can be in a state of free fall very easily. And as a consequence of that, the sole influence in a freely falling body's motion is gravity, simply because air resistance doesn't affect it significantly, and the only thing that would impact its motion would be gravity. And as a consequence of that, the acceleration of freely falling bodies is actually constant. In short, they will undergo UAM, or uniformly accelerated motion. On Earth specifically, that acceleration is equivalent to 9.8 meters per second squared, meaning to say the velocity of objects on Earth, if you allow them to be in a free fall state, they will change their velocity by 9.8 meters per second every second. Of course, it varies across planets, but for Earth, it's 9.8 meters per second squared for all objects as long as air resistance is negligible. In fact, there's this experiment where there's a ball and a feather that were dropped simultaneously from the same height. And they reached the bottom at the same time because it was done in a vacuum chamber, meaning to say, this is almost completely void of matter. So there's almost very negligible air resistance. There's almost zero air resistance in a vacuum. Therefore, you can see that they're accelerating at the same rate. So in short, objects accelerate at the same rate when air resistance is negligible. And when an object in a state of free fall, you can ignore air resistance, therefore, they will have the same acceleration. And again, that's 9.8 meters per second squared. Now, there's a frequently asked question. Does an object have to be in a vacuum for it to undergo free fall? The answer is no. Just like in this case, it can actually send a wrong message. Oh, does it have to be in a vacuum for objects to be accelerating at the same rate, which is 9.8 meters per second squared? And the answer is actually no. Because let's say, for example, if you drop a crumpled paper here on the surface of the earth, not in any vacuum, for example, whether artificial or real vacuum, like say, for example, moon. Okay, so if you let this crumpled paper fall on the surface of the earth, it can be in a free fall state, right? Why? Because if you look at the surface area of a crumpled paper, it's not that big, right? So it doesn't expose much of its area, therefore, it can easily ignore air resistance. So it's hard for air molecules to push it upward and prevent its downward motion or impede its downward motion. But this sheet of paper, for example, air molecules can easily affect its motion. The air molecules can push it upward as it tries to go down due to the gravitational pull of the Earth. So this one, the crumpled paper, can be in a state of free fall, but this open sheet of paper cannot. So they don't have to be in a vacuum. Objects don't have to be in a vacuum to undergo free fall. Their surface area or their mass can sometimes render air resistance negligible, and they can be in a state of free fall. So they don't have to be in a vacuum. Okay. Another example would be if you have a really heavy object. Let's say, for example, your phone. It's massive enough to ignore air resistance completely. And if you let it fall, even if you're not in a vacuum, of course, it's supposed to hit the floor straight down. So your phone, if you allow it to drop, it will be in a state of free fall. But don't do it unless your phone is shock proof. Okay? So to make it a bit more mathematical or to make you visualize it further, an object in free fall undergoes uniform acceleration, as mentioned earlier, and on the Earth, it's specifically speeding up at 9.8 meters per second every second, or approximately 10 meters per second. So, in this case, for example, you can notice that every after second, the object picks up a speed of 10 meters per second, and then another 1 second elapses. Then it gains another 10 meters per second. So from 10, it became 20. And then another 1 second interval, it picked up another 10 meters per second magnitude of velocity. Okay. And then on the fourth second, it became 40 meters per second. So we can see that every second, it speeds up by 10 meters per second. Okay. Just a clarification, Miss Leia, you said earlier it accelerates at 9.8 meters per second squared. How come this is showing me 10 meters per second change every 1 meter second, every 1 second? It's simple. This source actually simplifies it because it's easier to see the intervals or the increments if you use 10, right? Besides, 9.8 is approximately close to 10 meters per second anyway. But for stricter calculations, we're going to use 9.8 meters per second squared. So this visualization is just for simplicity. Instead of using 9.8 and then 19.6, for example, so they made it 10 meters per second every second. But the point is that here on Earth, objects do accelerate at a definite rate because of Earth's specific strength in pulling things towards its core. And for the graph of an object in free fall, of course, the velocity would be increasing at a definite rate, which is approximately 10 meters per second every second. Okay. Going forward, before we have discussed about horizontal UAM, and it's actually just similar to freely falling bodies. So in this case, if you can still remember this object increases the magnitude of its velocity by 5 meters per second every second. So the acceleration or change in velocity is actually constant. And that's the same thing that's happening to freely falling bodies like this one. This one, it's speeding up by 10 meters per second every second, similar to this, except that this one happens along the vertical axis. That's what you should notice. In our past examples, we've always dealt with horizontal motion, but this time we're going to deal with vertical motion or vertical phase of UAM, which is about freely falling bodies. So, in short, freely falling bodies can simply be considered as UAM or uniformly accelerated motion along the vertical axis. Okay? Now, there are three cases of freely falling bodies. It's very simple, nothing bloody. The first case is a dropped object. Okay? And there are a few things that I want you to remember whenever you know what case of free fall it is, because these things will help you in the mathematical part of the lesson. For example, for dropped objects, the magnitude of initial velocity is zero. Why? Obviously, simply because you dropped it. You did not propel the object downward. You did not give it an initial push. So it's starting from zero as the initial velocity. And of course, the sign would be none because there's no such thing as negative zero or positive zero, right? Okay. One example of that is in one of Taylor Swift's music videos, he actually dropped this phone in one of the scenes there. And that's an example of case one freely falling body because she simply drops it. She did not propel it for downward. She did not give it any initial downward push. She simply opened her hand to allow it to move downward on its own with the help of gravitational pull, of course. So that's an example of case one. Now, Taylor Swift would have been harsher, and she would have done case two free fall instead, which is thrown vertically downward. And when you say thrown vertically downward, it's kind of harsher for that cell phone's fate because case two free fall is thrown vertically downward, therefore the magnitude of the initial velocity is greater than zero, okay? Why is the initial velocity greater than zero for case two? It's simply because throwing vertically downward would mean you're giving the object a slight push downward, okay? So you're giving it a push, therefore, it's not starting at a zero velocity. It has a non-zero velocity the moment it was released by the object or whoever is holding it, okay? And for the sign of initial velocity, it's negative because downward velocity involves a negative sign. Lastly, we have case three of freely falling bodies, and that's thrown vertically upward. Okay. When an object is thrown vertically upward, one good example of that is those cheer dancers who are tossed in the air, for example. Why is it an example of a freely falling object? Because it can be misleading because of the term fall, right? Okay. This how come it's considered to be freely falling even if it's thrown vertically upward? It's simple because free fall is defined in physics as a state wherein only gravitational force is acting on the object or only gravitational force is affecting its motion. Okay. So even those cheer dancers or anything that are tossed upward, they're considered to be in a state of free fall. Okay. Of course, the initial velocity is greater than zero because obviously you can toss someone or something upward like that if you start at zero velocity. So you need an initial push. Okay. Actually, sometimes they have male lifters, right? They usually have male lifters for cheer dance groups because they're stronger, they can impart even greater initial velocity and toss the dancer higher up in the air. Okay, so but in either case, there has to be a non-zero initial velocity to propel the person upward in the first place. And then the velocity at the maximum height is zero because obviously it comes to rest at the maximum height because gravity is pulling down the object down. So if they toss her upward, gravity is like a villain. Gravity is like it's opposing the motion of the person or the object. So since gravitational pull is downward and their imparted velocity is upward, they're opposing each other. So what will happen is that the object will slow down. So her velocity was upward, acceleration due to gravity is downward. So that results to the object slowing down. And eventually at the maximum height, the velocity would be zero. Okay? Now for the sign, it's positive simply because it's thrown vertically upward, and upward is associated with positive direction. I'd like to go back with this one because okay, there's a frequently asked question here. Let's say, for example, for case 2 in free fall, why is it considered to be in free fall if you gave it an initial downward push? Okay, it's very simple. You only consider the object in free fall once you have let it go. Meaning to say, the minute you release the object from your hand, that's the time when you can only consider it to be in a state of free fall. So while you're still holding it, it's not yet in free fall. The moment you release it already, it's already in a state of free fall. But either way, the initial velocity would be greater than zero because even if you have let the object go out of your hand, for example, the momentum you have imparted on that object will be carried by the object as it falls down. Okay? And even further, it's gonna pick up even more speed due to the gravitational pull, pulling it downward. Okay, so that's how it works. Okay, so once again, it's considered to be in free fall once you have let it go. Okay, not when you're holding it. Okay, what else? The magnitude of the acceleration due to gravity is 9.8 meters per second squared. Because I'm only talking about magnitude, and when you say magnitude, it's just how much or how strong, for example, the gravitational pull is in this particular case. But take note that when we perform calculations on free fall problems, there must be a negative sign simply because this acceleration is caused by a downward force. And downward force would mean negative force, right? It's directed to the negative direction. Therefore, the acceleration due to gravity on Earth is negative 9.8 meters per second squared when you perform calculations. Okay? The magnitude is this, but in calculations, add a negative sign, even if it is thrown vertically upward. Okay? I'll clarify that further when we go to case 3. Like why is it still positive even if you throw it upward? So when we go to the math part, it will be discussed further. Okay, now for the sign conventions, displacement is positive if you measure it above the point of release. So all you need to do is to remember the Cartesian coordinate system and take note that above the point of release or above the origin, everything is positive, right? Okay, and if you measure the displacement below the point of release, it would be negative because in the Cartesian plane, the negative values are actually below the origin or the starting point. So that's it. And then for velocity, upward motion takes a positive sign, but if the velocity described in the problem is a downward velocity, it takes a negative sign. More of that in the next videos. For the problem solving part, you still have the same variables, v, v dot, or initial velocity, final velocity, displacement, acceleration, and time, but we'll add something a bit further. Okay, you should notice that we're adding subscript y for acceleration, displacement, and velocity, simply because we're dealing with motion along the vertical axis. So as simple as that. It's just for us not to be confused, especially when you start dealing with two-dimensional motion or projectile where there's y and x component. Okay, so we're adding y as the subscript because we're talking about vertical motion for freely falling bodies. The units are still the same. No need to expound this further. And then, of course, the four kinematic equations still apply. If you're wondering why these equations still apply, it's simply because freely falling bodies are also accelerating uniformly. So if they still undergo UAM, then these UAM equations should still apply to them. But since free fall motion happens along the vertical, we have a little addition in these equations, and that's just the subscripts like d sub y, v sub f sub y, etc. Okay, so those y subscripts are just to indicate that it happens along the y-axis or the motion is in the x-axis. Just a simple recall for the computation part, the first step for you to know which among those equations must be used is first you have to identify the given or the known values in the problem, and then identify the required to find or what you have to solve for. And then lastly, you have to identify the missing variable. Missing variable is the variable which is not the given, but it's also not the required to find. In short, it's not mentioned in the problem at all. Okay? And then lastly, you have to pick the equation that does not contain the missing variable in the problem. For example, displacement is the missing variable in the problem. You pick equation 1 because displacement is not there in that equation. As simple as that. I won't expound this for now because in the next video, we'll talk further about problem solving, specifically for case 1. So that's all for today. That's all for this video. Have a great day.